So we have started looking into module 5, wherein we have discussed the applications of DBS, satellite mobile, and other services. So we had started off with the introduction, right? And then we discussed as to what is the importance of satellite and the digital transmission technology. We also looked into the characteristics involved for different power requirements based on high power, medium, and low power. So accordingly, how we have to play around with the frequency levels are also given. Okay, and the application point of view is also discussed as to for what it is actually used. Here it's DBS, here it's point to point. Okay, and the EIRP range. So these specifications ultimately are looking for the goal of having high power and medium power and low power consumption respectively. Then here we spoke about the orbital spacing. Okay, now this is an important factor where each satellite are to be spaced apart. If they are not spaced apart due to the drifting of satellite, okay, there can be chances that these satellites might collide and have damage. Not only that, there can be even interference that can happen. Signals from satellite A to satellite B, okay, might interfere. Of course, the frequency of operation might be different, but there can be some static noise. Okay, there can be some EMIs, electromagnetic interference. Okay, so all this stuff. So it's always a safe bet to actually separate or keep these satellites apart and function. The general rule of thumb is that they keep about 9 degrees apart. Okay, so you can just see here we have spaced them about 9 degrees apart. So if you try and calculate, okay, between each, you'll have to keep adding, okay, 9 degrees, and ultimately you will be getting your next uh, angle, okay, in the next coordinate as to in which you have to place them. Okay, so I hope these concepts are understood by all of you, right? So these are different service providers, I can say, right, who are actually looking into um, or they are looking into the satellites. They're having their own satellites placed in different degrees or coordinates, I can say, right? Okay. So here in this, you can actually see that your partial contacts, okay, partial conus are here, then the full conus are here, and the partial conus is here. Now, what is all this? These are all like the contacts, okay? So they are placed apart. Each are referring to a specific degrees. Okay, so here it's about 61, then 101, 110, 119. Okay, the same degrees that we saw here previously. Okay, the same is mentioned here, but then with respect to spacing, and these dots are representing, okay, the satellites as to how it is put up in the space. So all this information, the numbers remains the same here as well. Okay, now the most important thing here is to concentrate on the power. Okay, now when we talk about the power, as you know, there are about 3 types, right? High power, medium power, and low power. So accordingly, for these various requirements, okay, our frequency inputs, the operation, the frequency operation also does change. Can someone tell me why is it so important to think of power? Is it a very essential factor? Yes, can someone unmute and respond? Is power such an important factor to think about? Anand? Anand, you're there? Adesh? Nisha? Kavya? Where do you think power is going
Sir,
to come?
for cost,
Cost. Okay. How is it? Substantiate your answer.
if power will be less, then cost will be also less. So,
How is it? Any other answers? Okay. Now having these power requirements, okay, thinking about how much power is needed, you can actually think of what systems to be connected, right? For example, if I want low power, then I'm very clear that what kind of frequency that I have to operate in. If the batteries that are involved in your satellites are not of that high capacity, okay, then I can think of operating them at a lower frequency. So deciding on what kind of power is an essential factor so that we can decide the other parameters as to in what frequency it's going to operate. Okay. And as I told you, power is a very crucial point because when there's no sunlight, when the solar panels do not charge, then what happens? It kicks in into battery mode. Okay. So once it's in battery mode, then the battery starts draining. So ultimately, if I'm using a high power frequency, okay, and I'm using underrated or less capable batteries, then what is going to happen? I might lose communication. Sometimes few eclipses can last for about 72 minutes, which is more than an hour, right? One and a half hour. So it should be able to sustain the communications that is happening from the base station to the satellite. So which means we are to uh, uh, take utmost care in calculating the power rating and how many transponders is actually required. Okay. Satellites intended for DBS have higher EIRP than for other categories. Okay. So those which are intended for DBS do have higher EIRP. So its range is from 51 to 60, which is substantially high. A communication satellite's transponder is a series of interconnected units that form a communication channel between the receiving and transmitting antennas. Okay, so this is a unit, okay, which helps us in communication in between the receiving unit and the transmitting unit. It is mainly used in satellite communication to transfer the received signals. Okay. So in the satellites, okay, in the communication with respect to satellites, this is actually used to send information whichever it has received. So that's the major importance of having a transponder. So it actually composed of a band limiting device, a low noise amplifier, and a frequency translator. Okay, so, so all these three are the important sections of a transponder. An input band limiting device, okay, which is an band pass filter. Okay, then why do we select the band pass filter? So that just only a range of frequencies can be allowed. Okay, whatever is our custom frequencies that is needed, only that can be taken. The other frequencies can be uh, you know filtered out. A low input noise amplifier, okay, which is LNA, low noise amplifier, designed to amplify signals received from earth station. So whatever signals are transmitted from our base station, that is sent to the satellite. Normally very weak because of the large distances involved, right? So as I've told you, those signals which are to be transmitted from the base station require higher power, right? And due to rain attenuation, due to various other factors, you can see that these signals reaching the satellites becomes too weak. Okay. A frequency translator are normally composed of an oscillator and a frequency mixer. So this is a combination of oscillator and mixer. So this converts from one frequency form to another frequency form. Okay, whichever signal is received to the frequency required for the transmitting signal. So it changes as per the requirement, the frequency of the signal. Then an output band pass filter, okay, which is also termed to be a power amplifier. So the power rating and number of transponders. Transponders are rated by the uh, power output of their high power amplifiers. So if they have higher ratings, okay, then they are considered to be of higher capacity, right? Okay. If in case their ratings are low, then it means they cannot handle higher frequencies, and it is very much well suited for low power applications. A satellite may carry about 32 transponders. Now, we have seen this in our previous discussions where we have used a transponder selection, okay, from the multiplexers and demultiplexers. If all 32 are in use, each will operate at low power rating of 120 watts. So 120 into 32, you can do the math. So that is the amount of power that is required to operate these transponders. The number of transponders can be reduced by doubling up the high power amplifiers, and each transponder operates at high power rating 240 watts. So if we want to reduce, okay, say for example, if we want to reduce from 32 to say 16, okay, to 16, then what we have to do, we have to increase the amount of power rating from 120 to 240, almost double. So it is like getting more work done from less number of transponders. The power rating has a direct bearing on the bit rate that can be handled. So the number of bits that gets uh, processed is also at a higher number. Okay. So ultimately, each transponder can be changed, okay, or it can be downsized if the frequency of or if the power levels are made higher. Okay. So that is one advantage of having a transponder. Now we'll be discussing about frequencies and polarization. The frequencies for direct, before we get into this polarization, I think all of you are aware we have this horizontal, vertical, and circular polarization, right? The frequencies for direct broadcast satellites vary from region to region throughout the world. So we cannot use the same frequency throughout the world, but different frequencies are employed in different regions of the planet. Although these are generally in Ku band. So Ku band is generally about 14 to 17 gigahertz range. So we will be utilizing this. So which means we need to have an international body which keeps track of these things, and who actually thinks of which country has to have this frequency, and country B has to have this frequency, country C will be going with this frequency. So accordingly, we will tune our transponders and the communications happen. Now, the reason why we do that is we do not want any interference. Okay, of course, we'll be using guard bands in between, which is about 4 megahertz of guard band, but still, that isn't sufficient. And also, we space them about 9 degrees apart. Even that is not sufficient. So the best way to counterattack this is to uh, use a unique frequency through which we can communicate. It's just like your cell phone number, right? Your number is unique throughout the world. Anyone can contact you on that number. If someone rings that number, okay, it doesn't mean that it starts getting connected to 2 3 people in the world, right? So so that is the uniqueness. So we will be operating frequency, uh, okay, which is different from each country. High power satellites, which are primarily used for DBS, the uplink is generally high, as I told you, because we need higher frequencies to transmit from the base station to the satellite. Can someone tell me why is it that you know we need a higher power for transmitting signals from the base station? Why is it so? I want you all to discuss. Let it not be a single way class. Let it be an interactive class. Yes, Suhas. Suhas, Swaroop, Satish, Saimanti.
So,
Yeah, go ahead.
transmitting from the base station, for transmitting from the base station, the power needs to be high, so
Okay.
that while in the transmission powers, there won't be any losses.
Okay. Now, can you tell me why it needs to be high? Fine, I agree it needs to be high, but why is it? Always keep in mind, when we operate at higher frequency, the amount of interference, the amount of disturbances will be less. Okay. Now, since we are transmitting signals, okay, probably 40, 50,000 kilometers apart. So, there is to be uh, signal traveling with lot of disturbances, okay, with lot of obstacles, I can say. Okay, it's just not a clean line of sight, right? So it has to pass through clouds, it has to pass through the rain, rain droplets. Okay, it has to pass through. See, once it hits the clouds, okay, that's where the major dispersion of the signal happens. Okay, where the signal strength is reduced drastically. So in order to keep this in check, what we do is we try to make sure that we operate at a higher frequency, so that even if there are few obstacles, okay, so I hope this information was clear to you as to why we are going ahead with having less frequency for downlink. So ultimately, we should make sure that our frequencies, which is used for uplink, needs to be higher. Okay, and the downlink range, as you can see here, is from 12.2 to 12.7. For the downlink, okay, this problem doesn't occur, wherein it doesn't require actually higher frequencies. So that is one advantage, wherein we can save a lot of power while transmitting information from the satellite. So this is for higher power satellites. So questions can be asked, okay, with regards to higher power satellites. What are the levels of frequencies, and what is the primary utilization of these satellites? You can either refer to this, or you can go back to the tabulation, okay, wherein here you can actually uh, write these points with respect to high power satellites, and these for medium, and these for low power satellites. Either you can either use this tabulation, or you can use this explanation here. Okay, so depending on the marks, you can decide which answer or how you can formulate your script. Medium power satellites also operate in Ku band at 14 to 14.5 gigahertz uplink. Okay, so you can see that here it's a little lesser. Okay, so it's about 14.5, and here it's about 17.5. So the frequency of operation is actually coming down. And the uplink also does change, right? For uplink here it was about 12.5, right? But then here it's about 11.5. So the uplink also does change. The primary use of these medium power satellites is that it can be used for point to point, and also it can be used for DBS, okay, which is direct broadcasting satellite service. So this will be in the form of your communications or entertainment, to be specific, right? So the available bandwidth, um, which is uplink and downlink, is seen to be about 500 megahertz. So in this 500 megahertz, we will be using 32 transponder channels, and each will have a bandwidth of 24. Now, if you multiply, okay, if you multiply 32, okay, with 24, can someone tell me how much we are coming up with? Yes, how much are we coming up with? Any answers? We will be coming up with 768 megahertz. Okay, but that's not possible because we have only 500. So in that case, what we will do, we will uh, we will try to separate them in the form of odd and even, just like how we did before, so that we can utilize the bandwidth in a much better way. Along with this, we need to even add the guard band as well. So the bandwidth is sometimes specified as 27 megahertz, but this includes 3 megahertz. Here we are not using 4, but we are using a 3 megahertz guard band allowance. So that is 24 plus 3. Okay, so that gives rise to 27 megahertz. So each transponder will at least need 27 megahertz, right? Therefore, when calculating bit rate capacity, 24 megahertz is only used because that is the only frequency employed for each transponder, right? Right. So continuing our discussion with regards to frequencies and polarization. So a total of 32 transponders requires the use of both right-hand circular polarization, RHCP. Most repeated question, it will be asked many times. Okay, it has been asked many times in your examinations. Okay, so RHCP and LHCP. So we will be using a circular polarization here with respect to right-hand side and left-hand side. So before you could understand, just see the diagram here. Okay, so here you will be using this uplink and downlink. Can someone tell me what kind of satellite is this? Is it high power, or is it low power, or is it medium power? Yes. What kind of satellites is it?
It's a high power satellite.
Yes, it is high power, because you can see that we have about 17 gigahertz range. Okay, so this is 17,000, so which means 17,000 megahertz, which means it's about 17 gigahertz, right? Okay, so you can see that we have arranged it in the form of odd and even, right? So initially we will be having 1, 3, 5, okay, 7, 9, and so on and so forth. Here we'll have 2, 4, 6, 8, 10, and so on. So ultimately, these 32 transponders are accommodated, and due to which, okay, we can even sandwich in between. We can even sandwich in between the 3 megahertz guard band, okay, and efficient utilization of bandwidth is possible if we use this odd even concept, right? In order to permit frequency reuse, and guard bands are inserted between the channels of a given polarization. So you can see that guard bands are actually inserted in between. It's not that these squares are overlapping, right? There is a small distance that is between each transponder. A circularly polarized wave can be in one of two possible states: right circular polarization, in which electric field vector rotates in right hand sense with respect to the direction of propagation, and left circular polarization, in which the vector rotates in a left hand sense. Now this is important, okay, if in case a question is asked with regards to what is your left um, circularization, circular polarization, and right hand circular polarization. Okay, so this is with respect to the field vectors. So if it moves in the right hand side, electric field vectors, then we term it as RHCP. If the vectors rotates in left hand, towards the left hand, then it's called a LHCP. Okay, so this is going to be the diagram wherein you'll be employing different frequencies, and these are separated, okay, in the form of your odd and even. Can someone tell me what is this region 2? What region are they talking about? Is it referring to something?
It is the range of frequency bands.
It is actually, the countries and the continents are given different regions. Okay, so if you remember, in our initial modules we had discussed about the region wise separations. Let me just pull it up if possible. In our initial lectures, you can recall, region 1 was given to some countries, okay, and region 2, yeah, okay. So this is what I'm talking about, wherein region 1, 2, 3. So when I say region 2, then it's actually referring to the Greenland and the Americas. Okay. And region 1 is referring to Europe, Africa, and Mongolia. So we fall under region 3. Okay, Asia, Australia, and Southwest Pacific. When I say region 2, it means it's referring to North and South America. So I hope you would have remembered these concepts, right? Okay. Okay. So region 2 is actually referring to the Americas and Greenland. So the whole world is divided into 3 regions. So each region will be given a separate frequency allocation, and we have to use them accordingly. So we have to again discuss with the neighboring countries as to in which frequency range that they are operating. And ultimately, once that is, we are clear with what we are going to do, and the neighboring countries also uh, can get along and use the different frequencies. Now, talking about the transponder capacity, okay, we have the 24 megahertz bandwidth. Okay, so this will be our last slide for discussion today. So each transponder is about 24 megahertz bandwidth, and 3 megahertz is used for the guard band, as you all know. The DBS television is also called DTH. Okay, so the one that I was telling you, which is used for the entertainment purposes. Okay, right. Now this requires many more channels, and this requires a move from analog to digital television. So we cannot be in the analog mode, but we have to move to a digital mode. So that is why most of our communications these days, I can say about 90% of our communication these days happens in the digital format. Okay. The reason why is quantization is easy. Okay, you can analyze signals easily. So it's all with zeros and ones and different modulation schemes, modulation techniques. Okay, then you are very much aware with the spread spectrum techniques. All this can be employed, right? Digitizing the audio and video components of television program allows signal compression. Okay, so this is important. Signal compression is what we are talking about. Now, even if the signal is compressed, okay, the quality will almost remain good. Okay, but this doesn't happen in our analog signals. Okay, the quality is drastically hit, and we cannot expect the same thing to happen. So hence the migration to the digital format. Now, having the signal compression, what is the advantage? We can send more information on a smaller bandwidth, right? So it's just like, if I tell you I have given you 1 GB of cloud space, and you are free to use, and in that scenarios, what we will do, you will try to compress videos, and you will try to store. If you use uncompressed videos, then each file might go beyond the GB, right? So in that case, we will try utilizing our bandwidth allocated very intelligently. So similarly, what we are trying to do here, we are trying to compress the signal, make it as small as possible in capacity, but then quality doesn't get compromised because of all this modulation techniques and schemes. And we try to recreate or reconstruct with the use of different algorithms, and this helps in actually saving the bandwidth. So because bandwidth is essential, bandwidth is important, okay, we need to make sure that this is greatly uh, taken into consideration. So once we have the bandwidth utilization done in a much proper way, okay, you can even refer to Carson's rule. Okay, Carson's rule, which talks about how the bandwidth is to be utilized. Okay, today once we are done with the lecture, okay, I want you to check out the Carson's rule for bandwidth. Okay, so there you will get an idea as to how it is dependent on your FM and FD. Okay, 2 times FM plus FD. The signal compression used in DBS is a highly complex process. So the signal compression is actually a very complex process wherein you have to make sure that the quality doesn't go, but then the size is actually reduced. So a lot of algorithms are there, okay, especially if you can just Google up, okay, algorithms used for signal compression, okay, you will get n number of techniques employed, right? So this is how communication happens between one transponder to another. Okay, and ultimately we have learned about how much of frequency that we are going to use, what is its application, what is the importance of signal compression, how it's going to impact the bandwidth utilization, and what is going to be done in cases of circular polarization, your left and right hand circular polarization. It's actually referring to the vectors which turn towards the right and left. Okay, so I think we will discuss the upcoming concepts, okay, with regards to the formula, the intermediate frequency, and also we will try to solve few problems uh, which would come associated with the formulas in our upcoming classes.